Namaskar and welcome to another video of Learn with Vishran Dastala. Today we'll learn about fractionation plates. In the past, the number of fractionation plates to be used was usually a trial and error proposition. At present, however, designers have several options to calculate the number of theoretical plates to be used for air fractionation or any other binary system. The options include the analytical method involving plate-to-plate equilibrium calculation, the McCabe-Thiele graphical method, and this graphical method. The analytical method is obviously the most accurate. Unfortunately, it is also very tedious and requires a lengthy procedure. In addition, there was originally a scarcity of data. Design engineer therefore abandoned the analytical method and opt for graphical method, which is simpler and quicker to calculate. The original graphical method was developed by this in France in 1922. This procedure was fairly accurate with enthalpy concentration diagram, but the lack of proper enthalpy diagram placed in this method at a disadvantage compared with the McCabe-Thiele method 1925. The latter method uses constant liquid and vapor rates or constant molar overflow throughout the tower. Constant liquid and vapor rates are based on the assumption that the components of the feed have about equal molar heat of vaporization. This assumption is acceptable when the components have comparable molecular structures and similar boiling points. In both methods, heat losses are considered negligible. Although the Poisson-Salvatore method may have proved a little more accurate than this other McCabe method, was found easier to use and was almost universally adopted for many applications such as air separation and fractionation. However, it is not accurate enough because enthalpy change or correction is important. Today, it has been almost completely replaced by the original plate-to-plate analytical calculation, which, with the aid of fast computers and more precise liquid-vapor equilibrium data, has been rendered quick as well as accurate. It is now possible to calculate in less than 1 minute the number of theoretical plates for an air separation column. Moreover, this permits the designer to start with a fixed plate feed or to place the feed at a given plate where the composition is more compatible with that of the feed. Once given the number of theoretical plates, it is possible to recalculate very quickly the number of actual plates by varying the efficiency to a more optimum level. Finally, the number of plates may be altered with input from experience with similar processes application. Nonetheless, it may be of interest to have an overview of the older method in order to visualize the parameter involved. Prior to the discussion of the number of plates required for the fractionation of air, some definitions are in order. First of all, a fractionation tower is rated accordingly to the number of theoretical plates contained as well as accordingly to plate efficiency. The theoretical plate may be defined as one of the produce an improvement in composition as existing and equilibrium between a liquid mixture leaving a tray and the vapor rising from the same tray. Plate efficiency is defined as the ratio in percent of the number of theoretical plates to the actual number of plates required for fractionation. Since ideal condition for equilibrium cannot be achieved in practice, one has to assume a certain plate efficiency. If the vapor has an initial composition of Y0 and has a composition of Y1 as it leaves the plate, compared with an ideal composition of Y2, then the plate efficiency is EFF equal to Y1 minus Y0 divided by Y2 minus Y0. In practice, the design engineers uses a specific efficiency for a given tray design. This efficiency may vary from one type of tray to another and from system to system, but an overall tray efficiency of 60% to 65% or better is not uncommon for air separation system. Finally, there is an experimental proven relationship between the feed state, whether it is a subcooled liquid and a saturated liquid, a mixture of saturated vapor and saturated liquid, a mixture of saturated vapor and supersaturated vapor, and its combination, the two product compositions, the quantity and quality of reflux, and the number of theoretical plates. Any of them can be calculated in if the other are known. In next video we'll be learning about analysis of flow of equipment. Okay, thank you for watching. See you in another video. Take care. Bye bye.